Welcome back to Macro Mornings. Today I'm going to talk about the new commands that we introduced recently for slipform paving calculations. So in this example here I've got a parking lot, and if we take a look at the parking lot islands, you'll see that the curves are not actually curves, they're chorded lines. And the data here isn't optimized at all for slipform pavers, so we're going to do some work on this data to make it useful for slipform paving operations for curb and gutter machines. So the first thing we're going to do is we're going to run what we call optimized line strengths. And optimized line strengths will take the curvilinear lines in both horizontal and vertical, and it will convert it into 3D curvilinear line work. If we look at this alignment right here, just make it profile view, there you can see there are lots and lots of nodes on this line. And if I exaggerate it vertically, you can see that the lines are not curved at all, they're just chorded, which is what you expect when you track this. Now when you're looking at curb lines like this, a curb and gutter machine could pave this line all the way down to here, even around this curved corner, but when it gets to this corner it would have to stop. So this is a sharp break that it has to stop at. And then when it keeps going down through here, it would stop again at this location right here, and then it would pave this last piece all the way down to the bottom of the parking lot until you get to this right angle. Then it would pave around this corner here as a separate line. So each of these lines has to be broken up, and you can see in each case, even though this is a curve, this is actually not fitted as a curve, so you're going to end up with a non-curvilinear vertical profile in the curb and gutter that you would pave with this line. So let's take a look at what happens to that line when we run the optimizer on it. So we're going to run optimize line strings here, and we're going to pick the lines that we want to optimize. And here we're going to say we want to use a reporting tolerance. Now it reports errors or deltas or changes to the line, and if you want to, you can report the midpoints of the lines as well. I'm not going to do that because there's lots of nodes in here anyway. And then we can say we want to optimize the horizontal, and you can specify maximum offset tolerance. In other words, when it fits the curve, how big an offset will you let one of the nodes be from the source lines before it has to change the number of curves or number of segments to fit. And then you can also limit the maximum radius of a curve so it doesn't create you very large circles for straight sections. We can do the same thing for optimization on the vertical. So here I'm saying if the angle of inbound and outbound slope varies by more than 30 seconds or 30 minutes of arc here, half a degree, then it's going to use a maximum offset tolerance here of 2/100ths and fit a curve length, a vertical curve of up to 10 feet in length in that corner. But it's also not going to generate vertical curves around these right angle corners. So when it gets to a right angle corner greater than 40 degrees, it's not going to form a vertical curve at these VPIs that go through these areas. And then we can say we want to generate line strings from this. We can put them on a layer of the same name as the source name. So this is the source name, and it's going to have an underscore or dash ls at the end of it. And it's going to give them the color cyan to show them differently to the red lines that we're starting with. And then here you could also decide you want to create alignments either way. But when we output this data at the end of the process to a format usable, for instance, on Leica slipform pavers, then it's going to generate an XML alignment for every one of these lines anyway, so you don't have to create alignments, you can just create them as line strings. And here we're going to say OK. Now it takes a few seconds to pass through all of this data, and at the end of it we're going to end up with 3D curvilinear line strings where the optimization has affected both the horizontal and the vertical curvature of the lines. And then we'll take a look at the analysis of that at the end of the process here. So all those lines have been optimized, and now in the reports section up here, it's telling us that for each line, it's got a maximum horizontal offset, maximum vertical offset. So here you can see it's fitted curvilinear feature lines to these perfectly, and then it's flagging anything that's out of tolerance with these characters here, and then down below it, if there's anything out of tolerance that you specified in these tolerances, it will be flagging it. So for each line, you can see it's fitting the line, there's nothing out of tolerance in any of these. You can see that it's doing a pretty nice job of all of this. If it does find a tolerance error, it's going to tell you at what station it is. So here at this one, it's got a height tolerance of 2/100ths at this particular station. So if we can find that line, we can go find out where on that line at 1166 is this tolerance bust here. And then line string 5, we're doing the same thing. So each line we analyze it both horizontally and vertically. And in this one here, we're starting to see some tolerance busts here within the 200ths that we specified as our limit. So these are the things that it's telling us are changes in the elevation for the vertical optimization here. So these are vertical optimization pieces here. And you can see they're all within the 200ths that I specified at this point, and it's not flagging anything. But at least you get a full report of every single line, so you can go through these and check what happened. Now you can also check that, of course, graphically, and if you zoom in, you can see that the two lines are right on top of each other everywhere. But if I zoom down here at this line right here, you can see that the blue line here is a true curvilinear line. You can see it's got curve fitted here, and these are the segment endpoints. So we went from what was the original line, which had lots and lots of nodes through here, to a nicely fitted, curve-fitted line through these points here. I just want to undo what I just did there, because I just moved the point by mistake. And if we look at the vertical, if I go back to this one that we looked at earlier, for instance here, and take a look at the vertical profile of that, what we're going to see here now is if I stretch the vertical up, well, we've still got the angle break at that right angle corner right here, where it came into the corner here. You can see that's that point right here, where we told it we didn't want to, but at this corner, it's actually fitted the vertical curvature through here, and you'll see the same thing apply. At the other end, that's the angle break, but over here on the rounded corner, it's rounded it off, and within 200ths, it's making a nice smooth curvilinear line, which will look a lot nicer in the parking lot and give a much nicer fit and ride to the parking area as well. So here you can see there's a bit of a switchback curve, and it's fitted that nicely as well. So each of these lines is now ready for use in a paving machine. So how do we then break this up and make it usable for pavers? So the next thing I'm going to do is I'm going to turn off the original lines and leave just these curvilinear feature lines. And the next step we're going to do is we're going to run the explode lines command. This basically allows me to break up the lines at the right angle corner. So I'm going to say pick all these lines, and we want to explode them at large deflections where the angles are greater than 50 degrees. I'm just going to say apply to that. And so now what we've done here is we've now split this line at the right angle corner. So you can see we've split this one off at the right angles, we've split this one off at the right angles, etc. This one. So this is now all set up ready for the paver. And the next thing you need to do to this data is to extend the lines. So when the paver starts here, it goes around on itself. But to get it started, it needs to start back here, come in on the line bearing and slope. And so when it hits this point to start paving, it's at the right elevation and slope. Now the other thing is these lines can't wrap around on themselves either. So if you've got a line that starts over here, if we tell it we want to start 15 or 20 feet before the starting point, and that happens to cross over the line that it's going to pave itself, then it basically will trim it back and manage that for me. So I can say extend lines, and again we're going to pick all the lines in the project here, but we don't necessarily want to do all of the lines, so there's a couple of controls that we can put in here. We put in the extension length. We can say trim back crossing by 2 feet. That means if it wraps around itself, it's going to do that. And you can pick a minimum line length to extend. So in this case, I've got it set to 20 feet. So you can see that some of these lines haven't been selected because they'd be less than 20 feet in length, or they're closed lines. So here we can also say don't pave a closed line, or don't extend a closed line, because you can't have it extended back here, coming in on itself, and then going back on itself on the outside. So basically closed lines are not computed in that sense. You'd have to break them in some way to give it a start point and end point before you do that. And right now we've let that be the user, but these little short lines like this one, these would all be hand poured, so we wouldn't bother using a paver for those. And again, this is a closed line up here. So in this case, we set the parameters. We can say we want to maintain the grade coming into the line, and then say OK. And when we've done that now, you can see that we've extended all these paving lines. So if we take a look at that in 3D view, now you can see that we're taking the pavement lines and we're extending them so that we're holding the grade coming into the line itself. This one actually has a little nudge in it because it's got a little nudge at the end of it here. So you might need to check some of those sort of things if you don't like that. But you can see all the other lines are going to come in at grade, and you're going to be able to pave these lines for the machines. And now the last thing is we want to take this line work and we want to export it to a land XML format. It's a dedicated land XML for Leica pavers in this case. So in this case we can say export XML is the file name. So I'm just going to pop that up into the desktop so I can easily find it. Say save it. And at this point I can pick all the objects that I want to send out to the paver and say OK. And now it's writing me a land XML file with all those as 3D alignment geometry. So that's instead of the usual TBC XML exporter which outputs these as 3D line strings, in this case we're outputting them as 3D alignments. And again, this just takes a few seconds. As soon as it's finished now, we can just go find that file, open it up in an editor. You can see that all the alignment data has been output as an alignment, so they're all alignments. They all have a horizontal alignment, and they all have a profile which has got the vertical curvature in it. And that's your data now ready to go to your Slipform paving machine for paving operations. So that's just one use case of the optimized line strings for paving operations. We've taken what was a multi-hour or many-hour process of cleaning up line work down to a few minutes of work for a large project, and you'll find that the paving operations will be a lot smoother as a result. So if you're interested in looking at this further, please give us a call. Thanks very much.